Hey everyone, this is part 2 of organic chemistry. In the first one, I talked about hydrocarbons, alkanes, alkenes, alkynes, and halogenated organic compounds. And in this one, I'll talk about cyclical organic compounds, alcohols, carboxylic acids, and esters. A couple of other documents I'll refer to as well. This is your Science 30 data booklet. And if I just scroll down here to page 9, what it does have is a bunch of useful information for organic chemistry. So that is the title, in fact, at the top of this page. So I showed you a picture which was the homologous series of alkenes. So essentially this table that we do have here, so this again shows us the prefixes, organic compound prefixes. So meth is the prefix for one carbon atom, eth is for 2, prop is for 3, and so on. So for all of these here, they are strictly the alkanes, so no double or triple bonds. And there are no branches that we do have here. They are all linear, and we're just increasing the number of carbons and filling it up with the hydrogen atoms. Going all the way from the single carbon, methane, to the decane that we have with the 10 carbon atoms. What it also shows here that is also of use to us are the molecular compound prefixes. So remember that when we are naming branches, for example, if we have 2 branches that are the same, for example, a methyl branch on the same carbon, then we need to use the di to indicate that there are 2 of them. So we use the molecular compound prefixes for that. Also down below, we have the general formula for all of the different organic compounds that you need to know for Science 30. So again, the ones that we've talked about, alkanes, the general sort of formula that we do have here. So for whatever number of carbons that we do have, you take the number of hydrogens and times that by the number of carbons, add 2 in, and that gives us the overall combination of carbons and hydrogens for that particular alkane. Alkenes, remember, a double bond for the alkenes, and they give you some examples here of, in fact, the simplest ones that you could get for each one of these classifications. Alkynes, now we have a triple bond between carbon atoms. And the other ones that we did talk about, these ones down here, the halogenated hydrocarbons, where we do have something like the chlorine, the fluorine, the bromine, the iodine that are stuck in, and they're named as a branch. So this one here would be the chloroethane. So that's kind of useful in your data booklet. Another one that I'll show you here that we can refer to a little bit later. I also gave you this document here, Organic Compound Summary. So this is definitely kind of useful when you're learning how to identify the different classes of organic compounds and some strategies for how to go about naming them, and also properties that we do have for those particular organic compounds and some common uses of them. So this is what you're kind of looking for in the structure. So alkanes, no double, no triple bonds, nothing else that we have in there. Alkenes, double bond, alkynes, triple bond, and again, the other one that we already talked about, somewhere further down here. Oh, you actually don't need to know ketones anymore for Science 30. That's no longer in the program of studies, but the halogenated ones, they are. And one more that I'll pull up here before we get back to the naming of these other ones, this one here that I also gave you, a dichotomous key for the naming of organic compounds. And we can go and take a look at that a little bit later as well. So back to the actual naming. So again, this is a continuation of the previous lesson that we did have on organic compounds. So these ones here, the cyclical organic compounds is what we're talking about now. So now we have the carbons that simply form in a loop. So it can be the simplest one that we have here, which is with 3 carbons. So the 1, 2, 3 carbons. So because there are 3, it is a prop. No double or triple bonds, it's an ene, but it's in the form of a loop, and that's what makes it the cyclopropane. For Science 30, you don't need to be able to name or write the formulas for any of these, but you still need to be able to identify them. And they might give you some functional groups that we're going to talk about shortly here that are coming off of the cycle, and you may be asked to identify those. So in this case, we do have, as we can see, the cyclo or cyclo in front. You might have some branches, and you would just use the normal naming rules for those branches. This is one that you definitely do need to know about, the 6-carbon six-sided ring structure, where we do have alternating double and single bonds, and that's what it shows right here, the alternating double and single bonds in the six-sided 6-carbon structure. And this one here is what is referred to as a benzene. So you do need to know that name, the benzene. This is what it's showing over here as well. So the reason why they show this structure here is because it actually alternates between the different forms in terms of where that double bond is going to be. So if I just draw a couple of these 6-sided rings, at each one of these points, by the way, there is a carbon there. And so the benzene, we have alternating double and single bonds, but then it sort of switches over, and now the double bonds are here. And because this goes back and forth, sometimes they just use this circle here to represent that it is a benzene. So again, you won't have to label, or you won't have to rather name, like this one here is named, or write the formula for it, but you may be given some branches. So for example, it might have over here the Cl, and you would have to identify that as the chlorine branch or the chloro branch that we have there. You may have CH2, CH3, and you would have to identify that as the ethyl branch. And again, there are some other ones that we're going to see shortly here as well. If it is a branch, you might see the name phenyl. That's where we have the benzene that's coming off as a branch from a hydrocarbon chain. And we are going to come across a number of kind of important ones in terms of environmental chemistry, where we might have some of these compounds that form more complex structures, where we have more than one of these rings that are kind of joined together. And again, you wouldn't have to name them, but they are kind of significant in terms of environmental chemistry. So ones that you do need to know, alcohols. So this one here has what we call a functional group, which is an OH or a hydroxyl functional group. So this is a little bit different than the functional groups, or sorry, rather than the hydroxyls that we've seen in the past. These ones, they are not a base. So if we do go back and talk about bases for a minute, a common base, metal with the OH, which is sodium hydroxide. So in this case here, this is going to be a base because in fact, well, these are going to kind of split apart, increasing the hydroxide. And this is what's going to make the solution basic, and it's going to increase the pH. But that does not happen when we're talking about alcohols and the OH or hydroxyl group that are on the alcohols. The alcohols, they are liquid at room temperature, and we'll take a look at some examples here shortly. But if you think about alcohol in alcoholic beverages, well, it is liquid at room temperature, and that is the case with other alcohols as well. General formula that we have, so the R here, again, is just our hydrocarbon chain. And then somewhere, could be at the end, could be along the middle as a branch, we will have this OH, and that's indicating that, yes, it's going to be an alcohol. So naming of the alcohols, just like we saw before, start off just by naming it as we would with an alkane, an alkene, or an alkyne. Now the final E. So this one here, that's the final or the terminal E. What you're going to do is simply change it to an OL, just like the ending in the word alcohol itself. You do need to specify the location of that OH or hydroxyl group. And we do this by putting a number in front of the name OL for where that hydroxyl group is located on the parent hydrocarbon chain. And again, as with other branches, you count from the end that is closest to the OH, change it into the OL, and again, this is going to be taking priority over other branches that you do have. Sometimes you might see the OH as a branch, and if you do see this hydroxy, That's just indicating that it is a branch on some other compound that takes priority over the alcohol, which might be like some of the ones that we'll see later, like carboxylic acids. So let's take a look at a few examples here of some of these alcohols. Same pattern that I did before. Let me give you some formulas first here, and we'll write the name. And then we'll go in the reverse direction as well. Okay, so we have our hydrocarbon chain here. And now what I'm going to do is I'm going to stick on this one here, our OH. And let's put another branch in here as well. Let's put a C here. Okay, so once again, just as a reminder, I'm only putting the C's here. But what that means is that we still need to fill in the other 3 bonds, and we're just going to make the assumption that every single one of these is going to be a hydrogen. So just like we did before, let's start by drawing a line through our parent chain. Draw a line through the parent chain, and what I like to say is circle the branch and put a box around the functional group. So this one here is now going to be an alcohol. This one here, of course, is our methyl, YL, because it's a branch. 1, 2, 3, 4 carbons that we have. So the organic prefix for 4 is the bute. There are no double or triple bonds, so it is a butane that we're starting with in terms of our parent chain. So even though we have a branch that's closest to the left-hand side here, the functional group, the alcohol, takes priority over that. So we do start counting at the end, which is going to be the right-hand side, which is closest to that OH. So this is our carbon number 1, this is our carbon number 2, carbon 3, and carbon 4 that we do have here. So we're not going to name the alcohol as a branch, we're going to change the ending on the butane. And we're going to change that to the OL, but we also need to specify what carbon it is on. So in between the butane and the OL, we're going to squeeze in here the number 2, because that's the carbon that the alcohol group is on. And of course, we also have this methyl, and this methyl is on carbon number 3. So this is going to be a 3-methyl. So bringing this all together, we write the branch first. So it is the 3-methyl. No space in between here. We're going to write the bute, and then we squeeze in here the 2 and the OL, indicating that it's an alcohol. So this is 3-methyl bute 2-ol. Sounds kind of strange, but that is the format that we do use for these. Let's make another one a little bit more of a challenge here. So for Science 30, in reality, you're probably not going to get anything this difficult, but just to have a little bit of fun and show you how you can have these different functional groups and different branches in here, let's try this one. All right, let's give this one a try. So, very first thing that you do, well, I guess a number of different things you could do. We could start by taking a look at what is the functional group. So let's do that. We can see here that there is the OH. So that means again that this is going to be an alcohol. So somewhere we need to change the ending to OL. Longest parent chain. So if we go along this way and then up and zigzag along, that would give us our longest parent chain. So from here, we could either go up or we could go straight across. It ends up being exactly the same. Okay, that's our longest parent chain that we do have. So now we have some other branches in here. We have this branch and we have this branch. In other words, we have 2 of them, and both of them are the same. Both of them are ethyl branches. So somewhere in here, we're going to have a diethyl. Now, which end do we start counting at? We start counting at the end that's the closest to not the branches, but the functional group. So we have another branch here, which is a halogen, and that is our chlorine. So we're going to name that as a branch chloro. OH, closest to the left-hand side, so this is going to be our carbon number 1, 2, 3. So this is going to be a 2-chloro. 3, 4, 5, 6, 7. So we're going to have an ethyl that's on carbon number 5, and we're going to have an ethyl that's on carbon number 4 as well. So we are going to have a 4,5 diethyl. Remember that we go alphabetically in terms of the branches. So C comes before E. So we're going to name the chloro first. We have a 7 parent chain carbon. So that is a hept, and there's no double or triple bond. So it is going to be a heptane. But we also need to indicate where the alcohol group is. It's on carbon number 3. So this is a hept3-ol. Now we just need to write in all this other mess that we have here. So tying it all together, we're going to end up with a 2-chloro. Then we're going to have our 2 ethyls, and they're on carbons 4 and 5. And it is a diethyl hept3-ol. Big long one. Again, if you can name something like this, you're never going to get anything this challenging for Science 30. Let's do one more here. So let's just go in the opposite direction, where instead of starting with the formula, we'll start with a name, and then from that name, we'll write the formula. So let's make this one a 3-ethyl hex 2-ol. Okay, 3-ethyl hex 2-ol. Let's start with the parent chain. We have 6 of them. Hex is the organic prefix for 6. So we'll draw our 1, 2, 3, 4, 5, 6. We have an alcohol on carbon number 2. So let's start counting the left-hand side, carbon 1, carbon 2. So here, I'm going to put the OH. This is carbon 3, 4, 5, and 6. And on our carbon number 3, we have an ethyl. 1, 2, 3. So we're going to have an ethyl here. So just to make this one a little bit more complete, let me actually write in the hydrogens. So every single one of the carbons has to have 4 bonds. So we need to fill this first one in with 3 more hydrogens. This one just needs 1 more because we already have 1, 2, 3 bonds. This one has 3. We need 1 more. This one has 2. We need 2 more hydrogens. This needs 2 more hydrogens. One's on the end. If there's just a single bond between those carbons, then this one's going to have 3. These ones here, this is going to be a CH2. This one's at the end as well. So this one is also going to be a CH3. So those are the alcohols. So where do you find alcohols? Well, of course, alcoholic beverages, rubbing alcohol, and disinfectants as well, like we see right here, quite often do contain alcohol. Carboxylic acids. So carboxylic acids, these are organic acids. They are acids that are typically produced by living organisms, but they can be human-made, synthetically produced as well. So they contain what is referred to as a carboxyl functional group. So the OH, the alcohol, is a functional group. Carboxyl is another functional group. So a number of different ways that you will see it. A couple of them I'm giving to you here. It's always going to be at the end, and this is what we're looking for. We're looking for a carbon with a double bonded oxygen, and then a carbon that has an OH as well. So it's not an alcohol. There is this OH group, but also on that same carbon, there's a double bonded oxygen. So that's what makes this a carboxyl functional group. You might also see it, these carbons are connected here. You may also see it just written like this, where there's no line between the oxygen and the hydrogen. or you might simply see it like this, COOH. So all of these are indications that they are carboxylic acids. So in the cases of all acids, the reason why they're acids is because they donate their protons. So this proton right here is the one that's going to be donated. That's the one that's going to be donated when we do have an organic acid. So let's take a look at a kind of a simple example that we do have here. So it is the hydrogen that I just showed you that is on the hydroxyl group that's going to be released when it is dissolved in an aqueous solution, and that's what we have in this picture here. So this oxygen is attached to those double bonded carbons. Here we have 2 carbons. The carboxyl group, this is always carbon number 1. Okay, so the carbon that has the double bonded oxygen and the hydroxyl, that is always your carbon number 1, which means this is your carbon number 2. Because we only have 2, this is going to be an F in this case when we get to naming this organic acid. So right now the point is, let's show that this is an acid. So this here is going to be donated over to the water. And what we're then going to end up with is this here, which is acetate. It's lost the proton. And because we have the hydronium ion that is formed, this is what is going to drop the pH, and that's what's going to make this an acidic solution. So naming these, as always, start by naming it just as an alkene, an alkene, or an alkyne. Drop the final E like we did with the alcohol, but now we're going to change the ending to oic acid. Okay, so it can still be the ene or the ine, but the ending is going to be an oic acid. So let's take a look at that one that we just saw, which is the CH3. I will draw the line in here. C double bonded oxygen and an OH. Take a look at the parent chain that we do have, or if you want to identify the functional group first of all, it doesn't work. It works either way. So this is our longest parent chain. We only have 2 of them. So once again, this is going to be an F. There's no double or triple bond, so this is an ethene. But then we have this functional group. Again, this is our carbon number 1, not this one. Okay, the carbon that has the double bonded oxygen and the hydroxyl group, that is our carbon number 1. It's not going to make a difference for this example, but it will for future ones. So what we're going to do is we're going to drop this final E, and we're just going to add oic acid. So this becomes ethanoic acid, which is simply vinegar. So let's take a look at a couple of other examples here. Let's draw one that's a little bit longer, and let's throw a few extra things in here as well. Okay, let's give this one a try. So what do we have? Well, we have a functional group right here that's at the end, and you should identify that as our carboxylic acid. Longest parent chain, be kind of careful, it actually doesn't go straight across. We can get a longer parent chain going up this way. Always start counting with the carbon. That is where we have the carboxylic acid. This is our carbon number 1, 2, 3, 4, 5, 6, which means it is a hex. Let's throw in a double bond here as well. So let's say that we have a double bond, again, just to make it a little bit more interesting. So let's say that we have a double bond right in here. So now, not only is it a hex, it's going to be a hexene. And again, it's going to be a carboxylic acid. But for now, I'll just write it as a hexene. And we need to start counting. We don't go by the end that's closest to the double bond, even though it is closest to the carboxylic acid, but we always start where the carboxylic acid is. So the carboxylic acid now takes precedence over alcohols. It takes precedence over halogens. It takes precedence over other branches and over double and triple bonds as well. So this is a hex 2-ene because the double bond starts on carbon number 2. What else do we have? We have a branch here, which is a bromo branch, and it's on carbon number 2, so it's a 2-bromo. And we have this one here as well, which is a methyl branch, and it is on carbon number 4. So we have a 4-methyl. We're going alphabetic once again. B comes before M, so this is going to be a 2-bromo. No spaces anywhere here. It is a 4-methyl. Now is where it gets a little bit tricky. So now we have a hex 2-ene, but I'm not going to put that last E in here because it becomes oic acid. 2-bromo 4-methyl hex 2-enoic acid is what this one would be called. Let's do one as well, where we're starting with the name and writing the formula. So let's make this one a 3, actually let's make it a 3,3-dimethyl. Pentanoic acid. 3,3-dimethyl pentanoic acid. So the methyls, again, YL tells you that those are branches that we're dealing with, 1-carbon branches, but we're going to focus on how many carbons we have. First of all, pent is 5. So 1, 2, 3, 4, 5. It doesn't matter which end you make the carboxylic acid. So here, I'll just make it at the right-hand side. So here I'm going to have a double bonded oxygen and my hydroxyl group. So that is my carboxylic acid. This is carbon number 1, carbon number 2, 3, 4, and 5. And what we have is that on carbon number 3, we have 2 methyl groups. So I'll put one here, I'll put one up above, and that is now our 3,3-dimethyl pentanoic acid. Where do you come across these? Well, again, a number of them are naturally produced. So if you think about natural acids like citrus fruits, the lime and the lemon and orange juice, in our body, lactic acid produced in your muscles, that is a carboxylic acid. Acetic acid, vinegar, ethanoic acid, that is a carboxylic acid naturally occurring. So they can be used as preservatives. So to food, quite often they add citric acid. Quite often they also add lactic acid or benzoic acid. And all of these are going to drop the pH, and that helps as a preservative so the food doesn't spoil. And also an acidifier, simply to make the food more acidic itself. Last one that we have here, these are the esters. So these are formed by a reaction between the two previous ones that we just took a look at. So if you take a carboxylic acid like we have here, if you take an alcohol like you have here, and if they do react together, then what we're going to get is the ester in this case. So what is going to happen is we're going to take this hydroxyl group and this hydrogen, and they're going to be removed in the form of water, and this is the water that we see over here. And that's going to result in the remainder of the alcohol joining together with the carboxylic acid. It would be nice if this were flipped around the other way, because it's actually this oxygen and this carbon that are going to form a bond, and that's what we see right in here. So of this new compound, this is the portion here that came from the carboxylic acid. This is the portion here that came from the alcohol. So what you're kind of looking for now is you have, it kind of looks like 2 carbon chains that are separated by an oxygen in between, and this oxygen did come from the alcohol. So where you do have that double bonded oxygen, that's the one that was originally the acid, and it's this one here that's going to be our parent chain, and this is important for you to remember. That is your parent chain. This one here, the alcohol, it's going to be named as a branch. So this is our basic structure. This is what you're looking for. So again, this is a hydrocarbon chain, this is a hydrocarbon chain, but they're interrupted with an oxygen stuck in the middle. What you are going to do is this one, you're going to name as your parent chain. This one you're going to name as your branch. The one that's connected to both the double bonded oxygen and the oxygen in the chain, that's your parent chain. The one that's only attached to the oxygen in the chain, that's going to be your branch. Let's take a look at a couple of examples here for the naming. So once again, you're just going to name them as hydrocarbons. The carbon chain from the alcohol, again, that one, as we just saw, is going to be named as a branch, so it will have the YL ending. And the other carbon chain that came from the carboxylic acid, that's the one that's going to be named second as the parent chain. You're going to drop the final E from the hydrocarbon parent chain, and you're going to change it to OATE. Okay, so a few examples here that we can take a look at. So let's do 4 carbons here, starting off with. We'll have our double bonded oxygen. We'll have our oxygen sandwiched in the middle, and then one more carbon. So what we need to then determine is which one is going to be the branch and which one is going to be the parent chain. Where we have the double bonded oxygen, whatever carbon is attached to that, that's going to be our parent chain. This one here is going to be our branch. So this one here, there's only one carbon, so it's going to be a meth, and it's going to be a methyl. And just like all branches, you write those first. So this is going to be a methyl. 1, 2, 3, 4 carbons is a bute. There are no double or triple bonds, so it is a butane. So we're going to write in here methyl butane, only we're going to drop that final E, and we're going to write OATE, methyl butanoate is how you would name this compound. Let's do one going in the opposite direction. So let's make this one a hexyl ethanoate. As soon as you see the OATE, this is what you know. You know that there's a double bonded oxygen with a carbon attached to it, oxygen in the middle, and another carbon. So now we're just trying to figure out all the rest of it. So the hexyl is going to be this one here. So the one that's only attached to the single bonded oxygen. So hex means 6, so we're going to have 6 carbons. This one here is our parent chain. F is 2, so we're going to only have 1 more carbon here. Let me just go ahead and fill in all these sticks here as well to make sure that each one of our carbons does have the appropriate number of bonds. These would all be hydrogens that are on here. So this is going to be our hexyl as our branch. And these two here are parent chain. That's our ethane for our ethanoate. So these ones here, quite often there is an aroma that is associated with them. So esters are quite often, well, naturally occurring. So the aroma that you would find in strawberries, for example, does come from an ester, but we can also synthetically make strawberry flavoring or peach flavoring, and those are also esters. And fragrances, yes, they are esters that do have the fragrance that does go along with them. So I do just want to go back and remind you of a couple of these other documents that you do have one more time. So this one here, I didn't say too much about this one previously, but this is a dichotomous key. So how does it work? So this is really to help you learn. You can't use this for any sort of a quiz or an exam. So the first question that I ask is there a double bonded oxygen? So there are only two possibilities for that. It can either be an ester or a carboxylic acid. If there isn't a double bonded oxygen, well, it has to be one of the other ones. So then you're just kind of following through. So is the double bonded oxygen at the end? If that's the case, it's a carboxylic acid. If it's in the middle, then it's going to be an ester. Use the rules for following that, for naming the ester. Is there no double bonded oxygen? Well, what if there is still an oxygen? Well, then it's going to be an alcohol. What if there's no oxygen? Well, then it could be an alkane, an alkene, or an alkyne. And again, you might still have some of these halogenated organic compounds that are stuck in there as well. So use that. Again, this is your data booklet that you have. So in the previous lesson, once again, we saw the alkanes, the alkenes, and the alkynes, and the halogenated organic compounds. And in this lesson, what we did see are the alcohols, the carboxylic acids, and the esters. They give you the general formula. They even give you an example and how it is named for that organic compound as well. And just the one final one here, once again, to help you with the learning of organic compounds. So I give you all of them here as well. The one, again, that you don't need to know are the ketones. That should no longer be in here. You don't need to know ketones for Science 30. But the name at the end, the basic structure, some examples, some properties, and some common uses for those organic compounds.